Introduction to Quantum Information Processing. I'm Richard Cleave. I'm a professor at the Institute for Quantum Computing and the Cheriton School of Computer Science at the University of Waterloo. This is part 1, a primer for beginners. It is the first part of the course Introduction to Quantum Information Processing. The other parts are quantum algorithms, quantum information theory, and quantum cryptography. Here in part 1, I'm going to explain the basics of quantum information processing with intuition and technical definitions. To be able to follow these lectures, you will need to have a solid understanding of linear algebra and probability theory. But you do not need to have any prior background in quantum information nor in quantum physics. You'll see how information processing works on systems consisting of quantum bits. I will show you the kinds of maneuvers that are possible with quantum bits and how they can be used in some simple communication scenarios. Although the examples in this part are simple, they are part of a foundation. They will help you internalize the more dramatic applications in quantum algorithms and quantum cryptography that we'll be seeing in the later parts of the course. Think of this part as like learning how to ride a bicycle. You may ultimately be interested in competing in a famous race like the Tour de France, or in an off-road biking adventure in the Himalayas. But first you need to learn how to balance on 2 wheels. This is lecture 1. In this lecture, we are going to see how single quantum bits, called qubits, work. During the lecture, the following broad questions will arise. Is a qubit digital or analog? How much information is there in a qubit? If you feel that you're well past the beginner stage, please consider fast-forwarding to slide 11. There I consider questions about communicating a trit using a qubit, and there is some subtlety with that. By the way, the slide numbers are at the bottom right. Let's start with the question, is a qubit digital or analog? To begin with, consider what an ordinary bit is. To store a bit, we need some physical system that can exist in 2 separate states, say low voltage or high voltage. I'm abstractly representing such a system by a blue box. I have a little USB flash drive that contains 128 gigabytes. Think of the blue box as a flash drive containing just one single bit of information, a 0 or a 1. Now, I'm staying with you, but I'm going to get my image out of the way so that you can focus on the contents of the slides. You'll see me again later on. What's important are the operations that can be performed on a bit. We are going to think about a few simple devices that perform operations on bits. First, imagine a device that enables us to set the value of a bit to 0 or 1. We plug our bit into that device, and then we push one of the 2 green buttons to set the state to either 0 or 1. Suppose we push the button on the left to set the state to 0. Later on, we, or someone else, might want to read the information stored in the bit. Imagine a read device that enables this. We can plug the bit into that device and then push the activation button. This causes the bit's value to appear on a screen so that we can see it. A third type of device is one that transforms the state of a bit in some way. For example, for a NOT device, we plug the bit in, and when we push the button, the state flips. 0 changes to 1 and 1 changes to 0. This transformation is called not because it performs a logical negation where we associate 0 with false and 1 with true. Note that for this kind of operation, we don't care about seeing what the value of the bit is, as long as that value gets negated. Okay, that's more or less what conventional information processing is like, albeit with many more bits in play and more complicated operations. Next, let's consider an analog information storage system. It has a continuum of possible states, say any voltage within some range. We can abstractly think of the state as a real number between 0 and 1. The red box represents such a system, an analog memory. Imagine a device that sets the state of the analog memory. We plug our system into it. Suppose that there is some kind of dial that can be continuously rotated to specify any number between 0 and 1. Then we press the activation button, and the state of the system becomes the value that we selected. We can also imagine reading the state of such a system. Here the device has an analog display depicted as a meter. When we press the button, the needle goes to a position between 0 and 1 corresponding to the state. And we can also imagine an analog transformation that, when activated, applies some function from the interval 0, 1 to itself. For example, mapping r to r squared, or r to 1 minus r. Now the real numbers are something of a mathematical idealization. In any implementation, there will be a certain level of limited precision for all of the operations. But such analog devices can be useful even if their precision isn't perfect. Moreover, in principle, one could make the level of precision very high. The resulting system may be very expensive to manufacture, but it could contain a lot of information. Before considering quantum bits, let's introduce randomness into our notion of a bit. Let's call this probabilistic digital. Suppose that the state of our bit is the result of some random process. So there's a probability that the system is in state 0 and a probability that it's in state 1. Of course, the probabilities are greater than or equal to 0, and they sum to 1. Let's put aside the question of what probabilities really mean. I'm going to assume that you already have some understanding of this. Now imagine a new kind of device to randomly set the value of a bit, where some probability value between 0 and 1 is selected by rotating a dial, within some precision, of course. When we activate, the bit gets set to 1 with the probability that we selected, and otherwise it gets set to 0. Now, from our perspective, if we knew how the dial was set, there's a specific probability distribution with components that we'll call P0 and P1, and the state of the system is best described by this probability vector. But note that the actual state is either 0 or 1. We just don't know which it is, and the probability vector is a useful way for us to think about the state given what we do know. Notice that the probabilistic digital model has an analog flavor. There are a continuum of possible probability distributions. But although the set device for analog and the set device for probabilistic digital are superficially similar, after all, they both have a dial selecting a value between 0 and 1, what they actually do is very different. Suppose that later on, we insert our bit into a read device. After we press the button, the actual value of the bit appears on the screen. Once we see the value of the bit, say it's 1, we change our probability vector. The component corresponding to what we saw becomes 1, and the other component becomes 0. Let's refer to this change as the collapse of the probability vector. Note that if we activate the read device a second time, we will just see 1 again, as opposed to another independent sample. Just to be clear, what the bit contains is the outcome of the original random process for setting the bit, which in our particular example was 1. It does not contain information about the process itself. Also, if we didn't know what probability values P0 and P1 were used when the bit was set, then reading the bit does not provide us with those values. After reading the bit, all we can do is make some statistical inferences. For example, since we saw 1, we can deduce that P1 could not have been 0. This is very different from the analog model, where we can actually see the value of the parameter r using a read device. There are also transformations, like the NOT operation, and more generally, any stochastic matrix makes sense as a transformation. A stochastic matrix is one where each column is a valid probability distribution. Applying a stochastic transformation to a bit causes the probability vector to change according to the linear transformation that the matrix represents. Okay, that's what information processing with bits is like when we allow random operations. So, how do quantum bits fit in? Are quantum bits like probabilistic digital or like analog? In fact, they are neither of these. Quantum information is an entirely different category of information, but it will be worth comparing it to probabilistic digital and analog. Now let's see what quantum bits are. We'll leave the information about probabilistic digital on display. A quantum bit, or qubit, has a probability amplitude associated with 0 and with 1. Probability amplitudes, called amplitudes for short, are different from probabilities. They can be negative. In fact, they can be complex numbers, as long as they satisfy the condition that their absolute values squared sum to 1. In other words, the amplitude vector, written here with components alpha 0 and alpha 1, is a vector whose length is 1, a unit vector. Okay, that's a definition, but it's natural to ask, what do these amplitudes actually mean? I do not have a simple one-sentence answer to this question. Our approach to understanding this will be operational. What I mean by this is that we'll consider what happens to qubits when basic operations similar to set, read, and transform are performed. We'll develop an understanding of qubits by seeing them in action. Later on, it will become clear that, unlike with probabilities, the explicit state is not 0 or 1. It works better to think of the amplitude vector, alpha 0, alpha 1, as the explicit state. Let's make a note of that. In this one respect, quantum digital states resemble our analog system, where the explicit state is the continuous value r. Now, let's see qubits in action. We have our quantum memory, the purple box, containing a qubit. To begin with, imagine a device that enables us to set the state of a qubit to any amplitude vector. The device has two dials that we can rotate. Why two? Because there are two real degrees of freedom for all amplitude vectors. The amplitudes alpha 0 and alpha 1, which are complex numbers, can be expressed in a polar form in terms of two angles. Well, arguably there are 3 degrees of freedom. However, it turns out that one of them doesn't matter. So we can tune the two dials to specify any state within some precision, and then we press the activation button, and the qubit is set to the state that we specified. Next, the quantum analog of the read device is called the measure device. We are going to consider this device carefully. Recall that the state of the qubit is described by an amplitude vector. We'll first describe in words what happens during a measurement. The outcome displayed on the screen is either a 0 or a 1, with respective probabilities the absolute value of alpha 0 squared and alpha 1 squared. Note that this makes perfect sense as a probability distribution because these quantities add up to 1. Also, the amplitude vector collapses towards the outcome in a manner similar to the way that a probability vector collapses when we read the value of a bit. The amplitude for the outcome becomes 1, and the other amplitude becomes 0. Okay, let's see this in action. We press the button, and in this case, the outcome is 0. Also, notice that the state of the qubit has changed. Alpha 0 has become 1, and alpha 1 has become 0. The original amplitudes, alpha 0 and alpha 1, are lost. In this sense, the measurement process is a destructive operation. And there's no point in measuring the qubit a second time. We just see the same result again. It should be clear that measuring a qubit does not enable us to extract the amplitudes alpha 0 and alpha 1. In this respect, qubits resemble the bits in our probabilistic digital system. Considering these two operations, set and measure, you might wonder, what's the point of these amplitudes? Amplitudes are kind of like square roots of probabilities. But when we measure, the amplitudes are squared, and we get a probabilistic sample. So what was the point of taking those square roots? In fact, if we stopped with these two operations, qubits would be essentially the same as bits. But qubits are interesting because we can also perform transformations like rotations on amplitude vectors. Note that if you rotate a vector of length 1, it's still a vector of length 1, so the validity of quantum states is preserved. In fact, the allowable transformations are unitary operations, which are kind of like rotations, but include operations like reflections too. Together, these 3 kinds of operations are essentially the building blocks of quantum information processing. We'll see that all the strange and interesting feats that can be performed in quantum information and quantum computing are based on these operations and similar ones involving more qubits. Now, a comment about terminology. What I've been calling probabilistic is commonly known as classical. The word classical is a reference to classical physics that existed before quantum physics. So we have classical information and classical bits versus quantum information and qubits. So we have a basic picture of how qubits work. But there are a few details to fill in, and we'll spend a little time with that. And then we'll consider the question of how much classical information can be communicated using a qubit, starting on slide 11. There will be a surprise application, which is a concrete problem for which a single qubit can accomplish something that cannot be accomplished with a single classical bit. First, let's go over some notation and further terminology. Recall that the state of a qubit is its amplitude vector. The bra-ket notation, introduced by Dirac, is commonly used for this. These funny-looking parentheses with the angle bracket on the right side are called kets, and ket 0 and ket 1 are shorthand for the basis vectors, which are orthonormal. By the way, orthonormal means orthogonal and of unit length. These two states are commonly referred to as the computational basis states, and all other possible states are linear combinations of them. For quantum states, these linear combinations are also called superpositions. More generally, in higher dimensional systems, which will come up shortly, any symbol within a ket denotes a column vector. A bra is like a ket, but written with the angle bracket on the left side, and it denotes the conjugate transpose of the ket with the same label. Taking the conjugate transpose of a column vector yields a row vector whose entries are the complex conjugates of the original entries. A bra is always a row vector. The inner product of two kets is written as a bracket, or bra-ket, which can be viewed as shorthand for the product of a row vector with a column vector, which is the inner product of the vectors. Recall that for inner products of complex valued vectors, one takes the complex conjugates of the entries of one of the vectors. Now, let's look at unitary operations more closely. We'll see three equivalent definitions of unitary. Let U be a square matrix. The first definition is in terms of a useful geometric property. U is unitary if it preserves angles in the following sense. For any two states, there is an angle between them, which is determined by their inner product. If a unitary U is applied to each of the two states, then the inner product between the states does not change. In other words, the angle between the vectors remains the same. The second definition makes it easy to recognize unitary matrices. It's that the columns of U are an orthonormal basis, which incidentally holds if and only if the rows of U are an orthonormal basis. Let's look at a few examples of unitaries. As mentioned, all rotation matrices are unitary. It's clear that the columns are orthonormal. Also, the Hadamard matrix, whose entries are 1 over root 2, 1 over root 2, 1 over root 2, and minus 1 over root 2 is unitary, though it's not a rotation, it's a reflection. Further examples are the three Pauli matrices shown here. The Pauli X matrix is like a NOT operation since it swaps ket 0 and ket 1. It's also called a bit flip. The Pauli Z, or Z, is sometimes called a phase flip. We'll soon be seeing these particular operations in action. The third definition of unitary is useful in calculations and is commonly seen in the literature. A square matrix U is unitary if U star U is identity, where U star is the conjugate transpose of U. That is, the transpose of U with all the entries conjugated. An alternative notation for U star, commonly used in physics, is U with a dagger symbol in the superscript. Now, let's look at measurements again. Let our qubit be in some superposition of ket 0 and ket 1 with respective amplitudes alpha 0 and alpha 1. Then the result of the measurement is to produce 0 with probability the absolute value of alpha 0 squared and 1 with probability alpha 1 squared. And the state collapses to either ket 0 or ket 1, respectively. Let's look at this geometrically. We have a two-dimensional space with computational basis ket 0 and ket 1. An arbitrary state as a projection on each basis state. What happens is that the state collapses to each basis state with probability equal to the projection length squared. The geometric perspective suggests some potential variations in our definition of a measurement. For example, there's no fundamental reason why the computational basis should have such special status. We can imagine basing a measurement operation on some other orthonormal basis, different from the computational basis. For example, consider this orthonormal basis. Any state has a projection on each basis vector, and although the projection length squared are different for this basis, they still add up to 1. Our new measurement operation could be defined so as to project to each of these basis vectors with probability the projection length squared. One way of thinking about what unitary operations do is that they permit us to perform measurements with respect to any alternative orthonormal basis. We have our basic measurement operation, which is with respect to the computational basis. If we want to perform a measurement with respect to a different orthonormal basis, then we carry out the following procedure. First, we apply a unitary operation that maps the alternative basis to the computational basis. Next, we do a basic measurement. Finally, we apply the inverse unitary to appropriately adjust the collapsed state. So that's a nice way of seeing the role of unitary operations. They change the coordinate system, thereby releasing us from being tied to measuring in the computational basis. A final comment here is a footnote that there are more exotic measurements than this, where the state is first embedded into a larger dimensional space. A unitary operation and measurement are then made in that larger space. We'll be seeing these types of measurements later on, after we get to systems with multiple qubits. Now, let's consider a simple problem involving qubits. Define the ket plus state as a uniform superposition of ket 0 and ket 1, where both amplitudes are 1 over root 2. Define the ket minus state as a similar state with minus 1 over root 2 for the second amplitude. What happens if a qubit in one of these states is measured? For the plus state, since the square of 1 over root 2 is a half, the outcome is 0 with probability a half and 1 with probability a half. For the minus state, since the square of minus 1 over root 2 is also a half, it's exactly the same probability distribution. Now, suppose that we're given a qubit whose state is promised to be either the plus state or the minus state, but we're not told which one. Is there a procedure for determining which one it is? If I were speaking to you in person, I would pause now and wait for an answer. What you might do now is pause the video to think about this a little. Or If this is obvious to you, then please feel free to keep going or to skip ahead. Okay, so we want to distinguish between the plus state and the minus state. The first observation is that just doing a basic measurement, which is in the computational basis, is useless. For either state, the result will be a random bit with probabilities 1/2 and 1/2. There's no distinction. But since we can perform unitary operations, we are not shackled to the computational basis. We can apply a rotation with angle 45 degrees. This maps ket plus to ket 1 and ket minus to ket 0. Then we measure in the computational basis, which perfectly distinguishes between the two cases. Here's another question to consider. Suppose that we are given either the ket 0 state or the ket plus state. The angle between these states is 45 degrees. Can we distinguish between these two cases? You may pause the video if you'd like to think about this. The problem with distinguishing between the ket 0 state and the ket plus state is that they are not orthogonal. So there's no unitary that takes one of them to ket 0 and the other to ket 1. And in fact, there is no perfect distinguishing procedure. It turns out that two states can be perfectly distinguished if and only if they are orthogonal. I'm stating this now without proof, but when we get to the information theory part of the course, we'll see some tools that make this easy to prove. Although we cannot perfectly distinguish between the ket 0 state and the plus state, we might want a procedure that at least succeeds with high probability. What's the maximum success probability achievable for this? Think about what's the best orthonormal basis to measure in. I'll leave this question with you and continue. Remember one of the questions posed at the beginning? How much information is there in a qubit? On one hand, a qubit can be in a continuum of explicit states, so the amount of information needed to specify a state is huge, even infinite in the case of perfect precision. But the measurement operation is very severe, yielding only a discrete outcome, like a 0 or a 1. So we cannot read out the continuous value. Let's devise a clear question about storing information that we can analyze. A qubit can obviously store a bit, representing 0 as ket 0 and 1 as ket 1. But suppose that we wanted to use it to store more information than a bit. The smallest upgrade we could ask for is to store a trit, which is an element of a set of size 3, say the set containing 0, 1, and 2. Can a qubit store a trit? To make the scenario clear, suppose there are two parties, A and B, that we'll personify and refer to as Alice and Bob. Alice receives a trit as her input, and her goal is to convey that information to Bob. Assume she is only allowed to send one qubit to Bob, from which Bob has to extract the value of the trit. Can this be done? First note that sending a bit is not sufficient. But can sending a qubit outperform sending a bit? One idea is for Alice to encode the trit as one of the so-called trine states. These are 3 amplitude vectors in 2 dimensions with an equal angle of 120 degrees between every pair of them. This is as close to orthogonal as you can get when 3 vectors are constrained to 2 dimensions. When Bob receives the qubit, can he extract the trit from it by some measurement process? You may pause the video to think about this. Okay, since the three trine states are not orthogonal, there's no way to perfectly distinguish between them. For example, there isn't even a way to distinguish between the first two trine states. So Bob can't even perfectly distinguish between the trit being 0 or 1 using this approach. Is there any advantage to sending a qubit over sending a bit? To answer this question, let's begin by defining the average case success probability of a strategy. Here the underlying assumption is that there is some known probability distribution from which Alice's input arises. For example, it could be the uniform distribution where each trit value arises with probability 1/3. Then the average case success probability of a strategy of Alice and Bob is the weighted average of the three success probabilities. Here's a simple bit strategy. Alice receives her trit, and she encodes 0 as 0, 1 as 1, and 2 also as 1. Then Bob decodes 0 to 0 and 1 to 1. This obviously succeeds for inputs 0 and 1, but fails miserably for input 2. If the input is a uniformly distributed trit with probabilities 1/3, 1/3, and 1/3, then the probability of success is 2/3, which is the best possible for a bit strategy. There's a very famous theorem in quantum information theory called Hollywood's theorem, which actually dates back to 1973. I'm not going to state the theorem here, but very roughly speaking, it says that classical information cannot be compressed by encoding it into quantum information. In our scenario, a qubit cannot communicate any more information than a bit can. There's a simplified version of the statement due to Ashwin-Nayak. It's simpler to state and also simpler to prove. For our problem, it says that the average case success probability of a qubit strategy is at most 2/3. Thus, sending a qubit performs no better than sending a bit, which can also attain average case success probability 2/3. If there were different probabilities associated with 0, 1, and 2, the conclusion would be similar. There is an optimal classical bit strategy, obtaining the maximum possible average case success probability, and a qubit strategy cannot do any better. As long as the probability distribution of the inputs is known, the bottom line is that a qubit cannot outperform a bit in this context. This seems to settle the matter, suggesting that a qubit cannot contain any more information than a bit. But it's actually not quite as simple as that. All the discussion so far has been for average case success probability. What about worst case success probability? For any given strategy, this is defined as the lowest success probability for all inputs, instead of the average of the success probabilities. This framework makes sense if Alice and Bob have no idea what distribution Alice's input trit will arise from. Whatever strategy they come up with, the trit could be the case where their strategy performs the worst. Here's the classical bit strategy that we just looked at, whose average case success probability is 2/3. What's its worst case success probability? For the worst case instance, the success probability is 0. If the trit is 2, then Bob produces the wrong answer for sure. but it can be improved to 1/2 as follows. Bob decodes 1 randomly to either 1 or 2. This classical bit strategy has worst case success probability 1/2. Success probability 1/2 may seem like pretty weak performance. But if there were no communication from Alice to Bob, then the best success probability for Bob would be 1/3. So the bit strategy is achieving something. It's increasing Bob's success probability from 1/3 to 1/2. As I was preparing this lecture, I wondered what the optimal worst-case success probability is for a bit strategy. I couldn't think of any better strategy than the one given here. On the other hand, I also couldn't prove that 1/2 is the best possible. By the way, the model here is that Alice can probabilistically map her trit to a bit, and then when Bob receives the bit at his end, he can also probabilistically generate a trit from it. So Alice and Bob can both employ randomness in their strategy, but we assume that they have separate sources of randomness and that their random choices are stochastically independent. Their randomness is uncorrelated. Well, I eventually figured it out, and it was easier than I first thought. I also thought about the optimal worst-case success probability of qubit strategies. What's remarkable is that the worst-case success probability can be higher for qubit than possible with a bit. The advantage is not enormous, but this shows that there is a sense in which a qubit can store more information than a bit. And we now have a scenario where a single qubit can achieve something that a single bit cannot. Okay, so what are the maximum success probabilities for bit strategies and for qubit strategies? And how are they obtained? Well, I'd like you to think about this, and I'm posing these as challenge questions for you. Remember that for bit strategies, we're allowing random behavior for Alice and for Bob, but their random sources must be uncorrelated. Also, for the case of qubit strategies, there is some subtlety to this question. If you tackled this question, you should consider exotic measurements that I only mentioned in passing. Bob can add a second qubit in state ket 0 to the qubit he receives from Alice, and then perform a 2-qubit unitary operation, and then measure the 2-qubit system. Starting in the next lecture, we'll be discussing systems with multiple qubits. By the way, you shouldn't feel obliged to solve all the questions that I pose, but I encourage you to at least think about them a little. Even if you don't solve them, you'll probably learn something by thinking about them. Okay, let's end this lecture on these questions.